Welcome everybody, both members and non-members, to the BAA spring meeting replacement. We were going to be meeting up in Nottingham, but obviously due to COVID, we've had to curtail the meeting down to two talks on the net instead. So what I'd like to do is to welcome Professor Christian Koenig. He's the Professor of Astrophysics down at the University of Southampton. Just a bit of a background, that he did his degree at Southampton initially before moving on to do a doctorate in astrophysics at Oxford, then moved out to Baltimore for his postgrad at the Space Telescope Science Institute, where he was fortunate enough to be granted a Hubble Fellowship Scholarship at the University of Columbia in New York. After which he returned to Southampton as a professor and is now running the astrophysics department there. So without further ado, I'd like to hand you over to Christian. His talk is going to be Quasar unification via disk winds. And if I can try and get it right, it's phenomenology to physics. So over to you, Christian.
Thank you very much. Let me try and share my screen here with you. Here we go. So hopefully this will work. Can you see that okay?
I can see it fine, yes.
Excellent.
Yeah, it's not full screen yet. You still have it as in editor mode.
It should show screen now, is it? Still not? Let me maybe stop the share and just try one more time. Share screen. Yes. Hopefully this works better.
Yeah, that's better. That's great.
Okay. Yeah, so first of all, thanks for the invitation. It's always kind of a pleasure to talk to amateur astronomers. In fact, it's kind of funny that you have me talking about quasars because, well, I have a lot of interest, and I'm much more used to talking and working with amateurs actually in the area of cataclysmic variables and accreting white dwarfs and so on, which is another one of my favorite research areas. So in a way, when I got the email to talk, I was expecting it to be to talk about accreting white dwarfs or maybe X-ray binaries, but since I do dabble in quasar work as well, and since that was more the theme of this webinar, I thought, okay, I can talk about that part of my research, which is not something I normally talk to amateurs about. So hopefully this will make some sort of sense. I should just preface this by saying that, as always, for any senior researcher, I'm going to pretend here that everything I say is my work, when in reality it's been done by lots of other people, particularly my postgrads and postdocs. And in particular, the people worth mentioning here are Nick Higginbottom, James Matthews, Sam Axe, and Sam Mangum, who have really done most of the work that I'll talk about in the second half of the talk. So very briefly, what I want to do is, and I should say, I haven't really had a chance to practice this talk much or prepare it or give it before. So this is all a little bit, the timing of it, I don't quite know how it's going to work out. But the plan is that I'd like to have sort of two parts. One, it'll be sort of more of a general introduction into quasars and active galactic nuclei, what they are, what we know about them. And then in particular, this question of, as we'll see, they're an extremely diverse and heterogeneous population. And a lot of the work, virtually all the work that we do in this area, is kind of trying to unify them, to figure out what the common thread is that links them all. And I'll try to explain what that sort of common thread, what the picture is that we sort of typically have of these things, and then also, which is very much a phenomenological picture, which is essentially, which is just to say that we have a picture that kind of tries to explain the diversity we see in terms of essentially orientation angles, but without necessarily saying what the underlying physics is. And I'm going to then try and switch to suggesting that one way of perhaps interpreting these things and moving towards physics is by thinking about the central engine, essentially, or at least the signatures that we see emerging from disk winds emerging from these things. And then none of this will make too much sense yet, but that's the basic idea that I'd like to sort of suggest, that we should be moving from trying to understand the diversity, the apparent diversity of things, of these quasars entirely in terms of orientation without worrying about what's really going on, to moving towards a picture where we actually try to look really at the physics of how the spectral diversity actually emerges. And hopefully that will make more sense as I go through. And then in part two, and this is sort of everything in part two, I would say is kind of time allowing. I thought then I might actually give you a little bit of a sort of tour through just a couple of recent bits of research that we've done on this, and to give you a flavor, hopefully, of the kind of research that I and my group that we're doing to try and understand AGN and quasars, and to try and check whether this idea of unification via disk winds is actually viable. So rather than, so the whole idea is sort of part one will be this sort of maybe more general review talk to give you a sort of sense, but then in part two, what I was hoping to do is really give you a flavor of, well, how do we actually do this? How do we try to make progress in this area and test whether the ideas we have are actually right? And again, time permitting, I will give you a couple of examples of how we, in our group at least, do this, and what sort of results we've gotten. Okay, so let me jump straight into the intro. So first of all, what are QSOs and quasars? So the abbreviation QSO comes from quasi-stellar object. Quasar is quasi-stellar radio source. And the fundamental point here is that, and the reason they got their name is that in images, for example, they look like stars, right? Hence quasi-stellar. And the picture on the right is just a classic quasar. The lines point towards it, and you can see it looks no different than any other star in that image. We now know, of course, that they are at cosmological distances. They're highly redshifted. They're billions of light years away. And as a result, given how bright they appear to be, that must mean they're intrinsically extremely luminous. Okay, so typical kind of luminosities, powers are, you know, maybe 10 to the 38 watts. I mean, that's a lot of light bulbs. So these things are incredibly powerful. They're kind of more powerful than a typical galaxy. So that's what they are. And obviously a lot of the sort of a key question here is, you know, what is really powering these things? What, you know, we know that's what they are. We know that they appear to be point sources. They are great distances, but what's really going on? What powers these things? What are they? Now, one of the huge clues in this, and I want to go through this a little bit because I'll come back to this towards the end more, is you can learn an awful lot about all kinds of astronomical objects by essentially not just looking at images, but by splitting the light into its constituent wavelengths. Here's just a little illustration, right? You can do this with a prism, although typically these days we do it more with gratings, but it doesn't really matter. You take the incoming light, you split it up into its constituent wavelengths, and then you look at how bright they are as a function of wavelength. You create a spectrum. Overall, the spectrum, of course, the spectral range ranges from anywhere from the radio to really high, X-rays and gamma rays. But what I will be talking about today is mostly going to be focusing on visible light, which is just that little region you see here, sort of in the middle. If you can, I think you can probably see my cursor. So this region here, this is everything we see really. It's all just this tiny little region here. And then I'll talk a little bit also about the ultraviolet region. So in terms of angstroms, the visible is maybe from 3,000 angstroms to maybe 10,000 angstroms, and the ultraviolet is maybe from 1,000 angstroms to 3,000 angstroms. So it's slightly higher energy, but still not, X-rays or anything like that. Now, we can learn a lot about stars and other astronomical objects by looking at their spectra. And so one of the first things people did was with quasars too, is they basically looked at their spectra. They split the light up into its wavelengths and checked what they look like. And what was immediately found is they look incredibly weird. So the things on the left are quasar spectra. The top one is an optical one. So this goes from about 4,000 angstroms to about 10,000 angstroms. This is wavelengths we could actually see with our eyes. And in the bottom panel, I'm showing you an ultraviolet spectrum from about 1,000 to about 3,000 angstroms or so. And what you should hopefully see immediately and kind of notice is that, you know, these are interesting looking things. They're very blue, meaning they're very bright at short wavelengths. Their spectra rise sharp towards short wavelengths. And that's telling you that there's something very hot there. But perhaps even more importantly, they have these incredibly strong, broad lines, these emission lines is what we call these things, superposed on this underlying, you know, what we call continuum, this overall trend. So these are labeled here, for example, the Balmer series, this is what we call H alpha, and so on. But for now, I'll come back to how these lines are generated. But for now, just note how weird this looks when you compare it to a normal star. On the right here, I've just plotted a series of spectra for all kinds of stars. So these are just, this is the entire main sequence, essentially everything from hot O stars to really cool M stars. And you can see that their spectra just look nothing like this, right? Sure, you know, the hottest stars, O stars, have very blue spectra, but they have nothing like these crazy emission lines. Okay, so there's something really odd about this, and it's telling you already giving you huge hints about what must be going on there. Now, let me just briefly then talk about these emission absorption lines. And I'm not going to go into too much detail, but I think it's going to be really useful to understand a little bit more about how you make these lines and then why they're so useful and why we focus so much of our research on these lines. So these spectral lines, every one of these features, for example, here, like this feature labeled H alpha, right? What they really come from is, the way to think about it is, you have, say, an atom, maybe a hydrogen atom, let's say, and in this hydrogen atom, you have a nucleus and you have an electron, and the electron can only exist in certain specific orbits around the nucleus. So these are labeled, this is what we have here as these little circles. And essentially so the lowest energy orbits are the innermost ones and the highest energy ones are the outer ones. So the electron kind of normally wants to be in the lowest energy orbit, but what can happen is that an incoming photon, a particle of light, can hit it essentially, and that can, and then the electron can absorb this photon, and that gives it enough energy to move to a higher energy orbit. And so what happens here, if you think about this now in terms of what you would see when you look at this, is you would now see light that would have maybe reached you, but it now got absorbed by this electron. So at that very specific wavelength, which corresponds to the energy difference between these two orbits, there is now, you know, that absorption thing has sucked some energy out of the light. Okay, so at a very specific frequency, and that's the frequency corresponding to the energy difference between these orbits, you've just removed some light. Okay, and since we have lots of different orbits with different energies, there's a whole series of these particular transitions where you can, in this case, remove light. And that's what you would see as absorption lines. You would see dark bands at those specific wavelengths. And we see that, for example, in the sun. You can also do the opposite, though. So you can also have a case where an electron, which is in one of these higher energy orbits to start with, and if it falls down into a lower energy orbit, then it can emit an electron, a photon, a light particle, and then you see extra emission. And this is what must be happening in quasars, right? So basically, we must have a bunch of atoms floating around, which somehow have been excited into these higher energy levels, and then they emit radiation at these specific wavelengths, and that's what we see as these emission lines. So that's exactly how we make things like this. And here's just maybe a more familiar example to kind of put this and make this a little bit more concrete. What I'm showing you here is the spectrum of Vega. Actually, this is an amateur spectrum of Vega because, of course, these days, you know, amateur spectroscopy has become a really powerful thing. And it's just an example of the sort of thing that you might see. So for example, here we had, you know, these two orbits that we're looking at here are not that different in wavelength, in energy. So they create a relatively low energy, hence a relatively red transition, which is, I've labeled this as H alpha here, but that's just arbitrary. It's just a particular transition. And then maybe this over here, which is a more, there's a larger energy difference between these two things. So here we create a higher energy absorption line, which might be perhaps this one. And then again, there's this whole series of other possible lines. And so that's what you're really looking at when you look at these absorption lines. You're looking at either light being sucked out because of a photon or light particle getting absorbed and moving the energy to moving the electron to a higher energy state, or if it's an emission line, then you're seeing essentially a high energy electron decaying down and emitting a light particle. So hopefully that makes some sort of sense. Now, why do we focus so much on these things? There's lots of reasons why we focus on them, but one really important one is that they're incredibly useful. And the reason these lines are useful is because we know where they're supposed to be, right? So going back to this very briefly, we know where they're supposed to be because we can calculate what exact wavelengths, what exactly the difference in energy between these orbits is, and hence we know where these wavelengths should appear. We know exactly where this particular line should really be. Now, often we don't observe it at that exact wavelength, and the reason we don't is the Doppler effect. And it's just the same Doppler effect that you experience every day when a siren moves towards or away from you, right? If it moves towards you, you're sort of compressing the wavelength of the emitted sound waves, and exactly the opposite if the thing is moving away from you. And the same thing happens with light. And so with light, if a source moves towards you, the light is blue shifted, so the wavelengths are a little bit compressed. And so here's for example what the spectrum, let's say, of the sun would look like if it's just at rest, and each of these dark bands here is an absorption line. But if the sun were to move towards us very fast, then this would all be blue shifted. It would move to higher energies, right? Because the wavelengths are compressed. And if it was moving away from us, it would be red shifted. And that is an incredibly useful thing because, as you can now sort of guess, we can actually use the wavelengths we actually observe to tell us how fast the material that's emitting these lines or absorbing these lines is moving. So you can actually use the lines to tell you something about the motion of the material you're observing. And that's really powerful, right? So if I want to understand how quasars work, of course, it would be amazing if I could figure out, how fast things are moving and whether they're moving in circular orbits or whether they're moving whether it's just an outflow or an inflow. And I can hope to untangle this by looking at the shifts, the blue shifts and red shifts of these lines. And in fact, if you noticed early on here, note how broad these lines were, right? So this is telling you that these lines are really made from superpositions of many, many, many moving things, right? And each of them has its own little shift. And what this is telling us is that these very broad lines are sort of the superposition of lots of little things, some of which moving away from us, some of which moving towards us. And what we see ultimately over here is a broadened line profile. And so already the fact that we can, just measuring the width of the line, which you can do then in units not really of wavelength, but which is basically can be converted into units of velocity, you can basically say, oh, right, this line is, 5,000 kilometers per second broad. And that must tell me that the sort of material that's emitting them is moving at typical speeds of 5,000 kilometers a second, which is a very, very powerful thing. And if I see the line being predominantly blue shifted, I know not only that it's moving at 5,000 kilometers a second, but it's moving at 5,000 kilometers a second towards me. So that's really powerful. Okay, so that was just a little aside, but we'll come back. It's a really important aside because we'll come back to this later on. Now, what about active galactic nuclei, which are also in the title? Well, active galactic nuclei are really just like quasars. Also, they have one advantage, though. In their case, so here's a couple of images of a normal galaxy on the right and then of an active galaxy with an active galactic nucleus on the left. And hopefully what you can see is that the galaxies are basically the same, but the active one just seems to have a really bright point source in the middle, which you can tell by the diffraction spike. So they're very similar to quasars, these things, but in their case, it's just that the point source is a little less bright, and as a result, you can tell it's definitely located in the middle of a galaxy, and they have the same kind of weird spectra that the quasars do. So big emission lines on top of very blue continua. That was already a big breakthrough, right? Because in the case of active galactic nuclei, therefore, we sort of have a huge hint as to what they are. We know that they are something in the middle of galaxies. In quasars, originally, even that wasn't obvious, right? Because you just see a point source. But we've learned over the years that actually quasars are definitely also associated with host galaxies. It's just that quasars are so bright that they swamp the nearby light from their host galaxies. And the only way that we can usually see them then is by looking with something like the Hubble Space Telescope or something like that, which has such high resolution that it can actually see the host galaxy around it. And here's just some images from HST that HST took fairly early in its life, which were kind of important in absolutely definitively establishing that, in fact, quasars really are in the centers of galaxies. So you can see, for example, here in the top left, that looks a bit like a spiral, and you can see how hard this is, right? So this is with Hubble's resolution. If you blurred this out a little bit, it would just look like a point source. And so Hubble was necessary to tell that this is actually a very bright point source in this kind of spirally galaxy. But another thing that came out of this was that these quasars quite often seem to be in very disturbed looking galaxies, right? You can see here that these are all kind of weird looking things. They look almost like galaxies that are merging and things like that. And that too seems to be a bit of a thing in the sense that it looks like quasars like to be associated with kind of disturbed galaxies, which kind of makes you think that whatever, there's something fueling, right? Something in the middle of these galaxies, which is then becoming the quasar. So the quasars are maybe being fueled to some extent by these interactions. So this is a good time then to kind of, this is a great time now to kind of talk a little bit about what we really think is going on then. So today we feel pretty much 100% certain that quasars and AGN are in fact accreting black holes in the centers of galaxies. And how do we really know this? Like, why do we think that what we're seeing there is an accreting black hole? Well, it's a great excuse to show my favorite movie here in pretty much all of astronomy. And I'll show this again in a minute, but let me just talk about it first and then show it to you so that you can appreciate it as much as I do. So there had long been a suspicion really that, that's what's going on, that at the center of every galaxy, there is a huge supermassive black hole, maybe millions or billions of solar masses in the center of the galaxy. And of course, black holes are black, but the reason they can get bright is because if you dump lots and lots of mass onto them, then they can have accretion disks around them. I'll come back to that later. And it's really the disks around them that can get extremely bright. And certainly there was this idea, that was an idea that's been in astronomy for a long time. Of course, everybody's always slightly skeptical of the idea that you invoke a black hole, which you can't really observe. And so how do is that just like magic? Are you just invoking magic and you have really no idea if it's true? And it's not. And this is, I think, the absolutely most beautiful evidence for the fact that black holes really exist and supermassive black holes really exist, and they're in pretty much every massive galaxy. And it was obtained, it was actually, this was the subject of the most recent Nobel Prize in Physics. And it's basically from our own galaxy. What you're looking at here, let me show you this movie again now. Here, you're looking at a snapshot over many years of the motions of stars around the center of our galaxy, center of the Milky Way. And people did this with some really powerful telescopes, and they just followed, every year, every month, they would track this. And this is really astonishing, right? So let me just show this to you again, because it's just so nice. Okay, so the thing in the top left shows you when the image was taken, and this is literally just a movie made from actual astronomical observations. And the crazy thing here is, now that we zoom in on this, pay attention to the star that has the line attached to it, right? So after about, I forget, 10, 15 years, we actually saw this star make a complete orbit around something. And here's the thing. This something is not there, right? This is an ellipse. This star is orbiting something just like the Earth is orbiting the sun, except there's nothing at the focus of this ellipse, right? Nothing visible. But what's really cool about this is that just like you can work out the mass of the sun from the orbit of the Earth around it, you can work out the mass of whatever you're not seeing here at the center of this ellipse from the orbit around it. And when you do that, you find that there must be something hidden here, which is about 30 million solar masses, which is just incredible, right? So basically, we really know that these things exist. At the center of our galaxy, there is a concentration of, a huge concentration of mass, which doesn't emit any light and which is orbited by stars around it. So we really know that this is something that's happening. Our galaxy isn't particularly active, but every massive galaxy is doing this. And so what we think is happening basically is that in quasars and AGN, these black holes are just getting fueled at a really high rate. Mass is being dumped onto them at an incredibly high rate, much higher than in our galaxy. In our galaxy, virtually nothing's dumped on them, so they're quite faint. The black hole is quite faint. But in quasars and AGN, for whatever reason, mass is being dumped on them really fast, and so they emit a lot of light. So I'm not going to go into this too much here, but this is what we now think, is that every massive galaxy has one of these things, that typically the masses are between 1 million and 10 billion solar masses. And what's really amazing about this is that black holes are really compact, right? So the ratio of their mass to their radius is really high. So the sun, if we take the sun as an example, so take the sun as a reference point, so that it has a ratio of mass to radius of about 1, then a supermassive black hole with maybe 1 billion solar masses has a compactness which is about 20 million. So it's much, much more compact. And the point why is this important? It's important because simply dumping material onto something like this becomes just hugely efficient as a power source. It's just the gravitational potential energy that you release just by dumping a little bit of mass onto something as compact as this is enormous. You can actually release up to like 10% of the rest mass of mc squared just by dumping something onto a black hole, which is incredible. And that is really what we think powers quasars and AGN. That's what we think makes them so bright. Now you might wonder again how this is great. There's this much potential energy released when I dump mass onto a black hole, but how is it released? Why is it actually coming out? Why doesn't it just fall into the black hole? And the reason is that these black holes actually, when this material accretes, these black holes don't accrete just by stuff flowing in sort of in a spherical way, but actually they form these things called accretion discs. And these are the same kind of accretion discs that maybe you're more familiar with from cataclysmic variables, accreting white dwarfs and things like that. The same kind of process we think acts in these supermassive black holes. They form accretion discs around them. These accretion discs, essentially the material in their experience is friction as it spirals inwards towards the black hole, and that heats up the material, and it's that the thermal radiation from this accretion disk that we actually observe when we observe quasars and AGN. So that's what we really think is going on. Now, one of the huge puzzles that has been around for a long time in this area is that I've shown you these weird looking spectra, but actually what's odd is that there's a huge diversity of spectra. And so I'm showing you just a few examples here of different types of AGN, which look really quite different from each other. And there's additional differences. For example, some AGN emit lots of radio, others radio emission, others don't. And that's not clear why that is. So it turned out that this population of quasar and active galactic nuclei is, it's clearly a population. They're all accreting supermassive black holes, but there seem to be huge differences between them. And a lot of the work we've been doing in this area is trying to understand what's causing this apparent diversity. Like, why is it that they seem so different, even though presumably underlying it is the same physics? And the sort of prevailing paradigm people have come up with is essentially this phenomenological picture. I'm not going to go into gory detail here because it's just, a lot of this is just taxonomy. But the basic idea here is something along the lines of, what you see depends on which angle you look at. So if each of these green arrows corresponds to looking at a accreting supermassive black hole from a different angle, and depending on what that angle is, you will see different things. Okay, so for example, in this picture, the broad lines that I was showing you earlier are sort of depicted as coming from these little gray clouds right down here, which are apparently in this cartoon, just orbiting around this black hole somehow. In this picture, also the idea is the radio emission comes from a radio jet, and the idea here is simply that nobody really knows why some things have jets and why they don't. The best idea is that perhaps this is related to the spin of the black hole, but that's not really certain. But this picture is quite successful in some ways, right? So it explains that we should see quite diverse things depending on which angle we look at. And that's great. But you'll see that it is really just phenomenology in the sense that, there's no explanation in this picture for example, what the hell are these weird, clouds that are floating around? There's not really an attempt in this picture to explain what the physics of that is. It's just saying, if I have that and I look at it from different angles, then I'll see different things. And so the unification picture that we have at the moment, for the most part, is something like this. So, we see some quasars and AGN that have high radioluminosity or low, and we think that's linked to whether or not they have a jet or not. And that might or might not be linked to spin of the black hole. Then we see, another sort of division that we have is whether or not they are really, really bright or not quite so bright. The really bright ones we call quasars, the slightly fainter ones we call active galactic nuclei, and we think that's primarily due to how fast they're accreting, how quickly are you dumping mass onto them. There's probably another effect there to do with how massive the black hole is, in that quasars probably have somewhat more massive black holes. And then the biggest division that people often talk on is whether or not they have these broad emission lines I've shown you. I didn't really go into this, but there are some systems that do not show these broad emission lines. And we think that's because you're looking at them almost edge on. So your view towards these clouds that in this cartoon is blocked. So that's sort of the prevailing unification scheme. And you can see it's a very phenomenological picture. There's not much physics in there. But this brings us nicely now to something that's completely missing from this picture. And that is that we know about 15% of quasars actually show these extremely interesting absorption lines too. And so what I'm showing you here is, so the top spectrum here is a normal quasar. But then as you go into these other ones, you can see that they have these broad absorption features to the blue of the line, like this, where my cursor is now, for example. And again, about 15% of quasars show this. And this is really interesting because, again, this is not anything to do with the standard picture. Now, why this is fascinating is because, and again, I won't go into the physics here, but what's fascinating about this is that whenever you see this, whenever you see blue shifted absorption, you know immediately that what you're looking at is a line a feature that's formed in an outflow. And just again, without going into detail, but fundamentally what's happening here, if you remember what's happening with absorption in our little atomic picture, essentially what's happening is that if this was a star, but the same goes for a quasar, if there's an outflow around it, this star emits its radiation. And if there's an outflow around it, everything in this little cylinder here, if there is a transition that is capable of absorbing anything, right, then this will be light that would have reached you if it weren't for the absorption, but now it won't because it's been absorbed. And that this is all only happening, right, in material moving towards you. So it's only happening in blue shifted stuff. So whenever you see blue shifted absorption, you know immediately that you're seeing an outflow. So that's been extremely powerful, right? That basically whenever you see broad absorption lines like this, you know that, hey, these quasars, they must have these outflows, right? So that's very powerful. And in the orientation picture, what we think is happening is that perhaps, you know, maybe we have a picture like this, where we have this supermassive black hole here, we have an accretion disk, and maybe there's this outflow coming from the disk, and we see the broad absorption lines whenever we look through the outflow. As I've said, you know, this outflow must be coming towards me here, and if I look through it, I will see the broad absorption lines. But if I don't look through it, if I look at sort of more face-on angles, if I see these emitting disks more directly, then I don't see broad absorption lines. Now, in this picture, again, it's unification because the idea is that the outflow is always there. It's just that the signature of it, these broad absorption lines, you don't always see them. And so the missing ingredient in the unification schemes is really these broad absorption lines. And we now think that that's because, well, we have broad absorption line quasars if we look into the outflow, and we have normal quasars if you look across the outflow, so from more face-on directions. Now, this is already kind of cool, right? Because immediately you get some physics out of this. Namely, you can say, well, if 15% of quasars show this, that must mean there are 15% of sight lines that actually look into this outflow. And that's telling you straight away sort of how wide this outflow must be. So that's kind of a cool thing. Interestingly, and again, I probably won't have time to go into this much. Interestingly, only amongst the active galactic nuclei, the lower luminosity things, we don't see these broad absorption lines very often. There's a couple that have shown it, but mostly this seems to be just quasars. And again, I probably won't have time to go into this, but it's a fascinating thing that these broad absorption lines aren't always there in the lower luminosity things. But now, since we're talking about unification, what's really cool here, right, is that wouldn't it be nice if it wasn't if these outflows, since we've already said that the outflows must be there all the time, and it's just an orientation effect whether or not you see their absorption signatures. It's a pretty natural thing and kind of Occam's razor to then think, well, maybe it's actually the outflows that make the emission lines as well. And so this is actually, if you think about the title of my talk, which is From Phenomenology to Physics, I was complaining earlier that in the sort of standard picture, right, we just have these clouds floating around and we just say, well, these clouds somehow magically exist and emit the broad absorption lines. This is, of course, how you might go from that phenomenology to physics, right? If I could say, well, this is not really clouds floating around, actually, the emission lines come from the base of this wind, then I have an explanation for why there should be this emission actually. So this is a really kind of nice physical picture. And this is fundamentally the picture that in my group we're trying to test. Basically the idea that actually it's not just some random clouds floating around that nobody understands, but actually that no, it's one thing. There's an outflow from this accretion disk, and if you're looking into the outflow, you're seeing absorption lines. But even if you're not, the broad emission lines we see in every single quasar and every single AGN, they are still coming from the outflow. It's just you're not looking into the outflow. And therefore, what you see is an emission line. Now, very quickly, why should you care about these disk winds? Probably the most important reason you should care about these disk winds, other than just explaining the spectra of these things, is that we now know that the black holes in the centers of galaxies are really important. We know that they're not just important because they cool physics and, you know, supermassive black holes, but they actually affect how the galaxies evolve. And you can see this because it turns out there's relationships. The one on the right is maybe the more intuitive one. If you plot the mass of the black hole, which is on the y-axis here, against the mass essentially of the galaxy on the x-axis, what you see is that there is a nice linear relation between them. Essentially, the galaxy is always like 1,000 times as massive as the black hole. And that seems maybe sort of sensible, but if you think about it, it's actually very surprising, because the black hole only influences a tiny, tiny part of the galaxy. It really doesn't have any effect gravitationally on most of the galaxy. So then the question is, well, how do they know about each other? How does the black hole know anything about what the galaxy is doing? And how does the galaxy know anything about what the black hole is doing, right? These galaxies and black holes must have grown over time, but why on earth would their growth be coupled? Like, how would the black hole know that it should stay at always about a 1/1000th of the mass of the galaxy? So somehow there has to be some feedback between the two, how these two things are growing, and there has to be communication between the black hole and the galaxy. And outflows like this are the way in which we think this happens. Essentially, the black hole, for example, might produce a powerful outflow, which might clear the host galaxy of gas that it's currently trying to grow from. And so these sort of things might, for example, quench star formation. So it might be that once you have these powerful outflows, the black hole, even though it gravitationally controls very little of the galaxy, via the outflows, it actually controls what the galaxy is doing on really large scales. And I'm going to skip this here. Okay, so for the last few minutes, I just kind of want to now, so this has been my kind of race through quasars, AGN, and unification, and perhaps why disk winds might be a really nice solution for understanding more than just phenomenologically what's going on. And in the second part now, for the last few minutes, maybe just the last 10 minutes or so, I just wanted to give you a flavor of, the kind of work we do to test this idea. So specifically how do we test the idea that these outflows really are producing the crazy signatures that we see? And as you might guess, that's not so easy, really. Now, the way we do it in our group is by actually doing simulations. And what we do essentially is we build a model of what these outflows might look like, okay? And then we essentially try to predict what kind of spectra they would generate. What should we observe from these outflows? And then we ask, is what we observe a little bit like, what the observations actually are? Does that make sense? Can we understand what we observe in this context? So the simplest example would be, and probably the only example I have time to go into a bit, is it actually plausible? I claimed before that it would be nice if outflows could generate not just the broad absorption lines, but actually maybe outflows could even be responsible for the broad emission lines that you see in every single quasar. And that would be a nice kind of physics explanation for what's really going on. Now, that's something that we can test, right? If I can create a computer model of an outflow around a supermassive black hole, I can ask, if I look at my model from, one angle, do I see a broad absorption line quasar? And if I look at it from a different angle, do I see a broad emission line quasar? And that's exactly the kind of thing that we want to do. Now, the way we do this is basically like this. We set up in the computer, we set up a simple model just like this. So we basically have a very simplified picture of a quasar where we have a black hole in the middle. We have this accretion disk around it, which we model as infinitely thin. We model the outflows, which nobody really knows exactly how they work. We model them as simple bicones like this. And then we ask, well, okay, what happens if hang on, there we go. What happens if I observe this thing? And to do this, what we do is we grid this up. We create a numerical grid in the wind, and then we start firing photons, light particles through it, and we then observe them and ask, well, what would that actually look like then? And when you do this for a bunch of different parameters and a bunch of different models, you can then ask, well, what do you actually observe? What kind of spectra do you generate? And when we did this, again, our first question was, can we maybe understand why, or can we maybe explain the spectra of normal quasars, not just broad absorption line quasars, but normal quasars, just as outflows? in which case, they're formed in the outflows, but we're not looking through the outflow, so you don't see this light hasn't been removed from your line of sight, but it's still these the formation of these emission lines is still happening in the outflow. And what I'm showing you here is essentially the same model. So in black here, you're looking at the model we have. This is a particular model, right? And so what I'm showing here is just 4 different lines of sight through this model. So in fact, this is exactly these lines of sight that I've highlighted here. So here on the right is our schematic of our model. Here are 2 sight lines that look into this outflow, and then here are 2 sight lines that look more edge on, so they don't look directly through the outflow. And what you can see, I hope, is that these black lines, right, they have these huge absorption troughs, blue shifted absorption troughs, in this sight line here, which looks through the wind, also in this sight line here, which also looks into the wind. But if I now look across the wind, if I now look at angles that are more phase on, if you look at the black line, we see pure emission lines. Okay, there's no more absorption, but you do generate these emission lines. Now these lines are by no means, this is not a fit to the data. The colored things here are actual quasar observations, and I'm not trying to pretend that this is like a good fit to the data or anything like that. It wasn't intended to be, but it's sort of a nice proof of concept that this can actually work. So we have ideas for what might be responsible for the lines here, for example, being a bit too weak and so on. But as a proof of concept, this is pretty powerful. It means that these outflows can probably be responsible not just for the absorption lines that everybody agrees they are, but they might actually be responsible for pretty much the whole thing, for the emission lines as well, and maybe even for some other things in these systems. I probably will run out of time, but I guess I'm too tempted to, do I have enough time do I have another 5 minutes or so, or should I can stop at this point quite nicely.
No, Christian, go ahead. You've got 5 minutes and we'll take questions after that.
Cool, thank you. So the last thing I want to talk about then, since I have 5 minutes, is something that's really kind of cool as well, which is what you can do I've so far shown you what you can do by dividing light up into different wavelengths and then looking at, specific atomic transitions and blue shifts and red shifts and all that kind of stuff. But there's a different dimension that you can look at as well. You can look at the time dimension, which of course you as amateur astronomers, a lot of you I think study probably variable stars, you know all about this. And of course it's a really powerful thing. Now, active galactic nuclei and quasar, just like the kind of compact binaries that many of you study, you will know if you've observed them that they flicker all over the place, right? They by tens of percent typically, those kind of things. And quasars and active galactic nuclei also show this kind of flickering. We now think that this kind of flickering, this kind of almost random behavior, that's a universal feature of accretion disks. They all do this. It doesn't matter whether they are on scales that are 10 to the 9 solar masses or whether they are on scales of a white dwarf of 1 solar mass. So when you look at so the blue line here shows you a light curve of a particular active galactic nucleus, and again I would say that for those of you who observe, say, cataclysmic variables, this will look just like a cataclysmic variable light curve to you, I think, like a nova-like light curve, except the time scale is very different, right? This time scale here is on thousands of days, so the flickering happens, but it's a little bit slow. In a CV, that might happen on time scales of seconds or minutes. But what's amazing is that when people started looking at this more carefully, what we found was that if I then look at, let's say I look at also one of these emission lines we were talking about. So if I literally just basically create a light curve, but it's only made from one of these emission lines, what you find is that the lines track the continuum really well, right? The continuum here is just the overall emission from the AGN. But you can see that the emission lines actually track this extremely closely. Now, if you really squint at this, you might be able to convince yourselves that the red feature here, which is essentially looking at the light curve of this line, that it's slightly delayed relative to the continuum. Maybe you can just about spot that, if I draw a line down from here that this dip here is slightly after this dip. And this is universally true here. Here you can see too, this peak here, and then this one is slightly delayed. And so this always happens, that the lines seem to actually lag the continuum. And the way this happens is basically, the way we understand this is basically like this. We imagine, let's go back to this crazy cloud picture just for now, because it's kind of a nice little simple picture. What we think is that, we have a bunch of clouds, imagine a bunch of clouds floating around. We observe here from the right. These clouds have various velocities, and they have various distances from the central source. Okay. And so because they have different velocities, what I've illustrated here with these arrows is just that this one has a net motion towards us, and this one has a net motion away from us. And this one here might be orbiting, but it has no net motion towards or away from us. So now if this central quasar emits some light, right, and if that reaches this first cloud or the second cloud or this third cloud, right, there's a certain delay that then it'll basically take different amounts of time for the light that has gone via this cloud to reach us over here on the right. So for this cloud in the middle here, right, there's no delay at all, right? This path moves directly towards us. But if I want light to first reach this cloud up here and then us, it has to travel along a path, and that means is lagged. Okay. And then this one, the same thing. And so these ellipsoids here, or paraboloids really, these correspond to sort of constant time delay surfaces. But don't worry too much about the details here. The point here is now really that if I imagine this quasar emitting some light, a pulse, and then I observe this pulse, and then this cloud here reprocesses this, let's say absorbs or emits as a result of this pulse. Let's say it emits as a result of this pulse, and I will see an emission line, in this case at zero velocity, because there's no net motion towards or away from me, and I will see this particular line happening without any delay, right? But that same pulse takes a little bit longer to first reach this cloud, and then the emission from that cloud reaches us. And so at some later time, I now see a blue shifted component here. And it's blue shifted because this cloud is moving towards us. And then the same is true over here. Just now, it's even longer delayed because this light travel time is even longer, and this cloud is moving away from us. So therefore, this is redshifted. And you can see now that by observing these lines as a function of time, you can do an incredible job of essentially unentangling where the clouds must be around the black hole and how fast or what direction they are moving. So this sort of like a time-resolved spectroscopy is actually an incredibly powerful tool to try and untangle what is actually going on. What are these clouds? What is actually happening in this medium that is producing these lines? And fundamentally, the way to think about it is that the lag that you see fundamentally is just a measure of how large the region is. So if I see a lag of one day, then I know that the characteristic size of that region must be about one light day. And so that's really powerful. And people have used this already very much to essentially figure out masses of black holes, because once you do that, you can basically say, well, if I have the size of the region from measuring the lag, right? And so if I measure a size of, let's say I measure a lag of 1 day, and then I measure, I can then say that the size of this region must be about, 1 light day. Well, I also can, since it's an emission line I've measured, I can also say, well, this emission line is maybe 5,000 kilometers a second broad. And if I combine these things and basically say, well, very roughly speaking, I expect this to be related like for Keplerian flow or something, then you can use this to estimate black hole masses. And people have done this, and it's really powerful. Over this here, if you compare essentially, this is called reverberation mapping. If you compare the masses estimated that way to other masses, it works incredibly well. But for the last minute here, let me just show you what we've been doing about this, because actually even this is only partial information. I showed you in the little cartoon that you can actually decompose this into velocity as well, right? If I just go briefly back to this, if it ever works, which it doesn't. Sorry, I probably can't go back. So let me forget that. So if I showed you that I can actually tell whether the cloud with lag 1, for example, is moving towards me or away from me, right? Because it's either blue shifted or red shifted. So actually, I might expect I can monitor not just the overall lag, but I can monitor the lag as a function of wavelength and hence as a function of velocity. I can actually figure out that, for example, the blue part of a line, stuff moving towards me, is lagged more or less than the red part of a line, which comes from stuff moving away from me. And so that's really powerful. And that's only beginning to be used now. And what you can do is make actually these sort of crazy so-called echo images. And again, I'm just going to give you a quick flavor of this. The idea here is what you're looking at here in the bottom panel here. Let's say take the top one here. In the bottom panel, you're essentially looking at a line profile, just like the kind of lines we looked at before. This is the line profile you might expect from a disk, just a rotating disk. And you can see that it's double peaked. It has these, it has blue stuff over here. It has red stuff over here. And that's more or less what we'd expect to see. And it's broadened by maybe 5,000 kilometers a second or something. But what we can also do is basically ask, well, stuff here at 5,000 kilometers a second, what's its lag? And that's what we do in this image here. We can basically, in the y-axis here in the top, we measure time lag. And so it's actually not even a single lag, but stuff at 5,000 kilometers a second comes from a range, comes from a range of lags between about, maybe 5 to 10 days or something like that. Whereas stuff here in the middle, right, comes from a range of lags anywhere from maybe 0 to 100. And that's really powerful information. And these images basically encode what kind of stuff you're looking at. Are you looking at a disk, which is what the top image looks like? Or maybe here in the bottom image is an example of a simple outflow, right? And in the simple outflow, what you expect is the blue stuff is leading the red stuff. And so the idea is that we can use this to figure out whether or not, say, this line forming region is an outflow, an inflow, or a disk. We can construct these images, and from that, we can figure out what actually is happening physically in the region that's producing this stuff. And schematically, this is what people do. We basically say, well, if the blue parts lead the red parts, then it's probably an outflow. If the red parts lead the blue parts, then it's an inflow. And if it's sort of symmetric, then we think it's probably just some sort of disk or something like that. That's roughly what we think. But what we've done with our code, we can actually do this with our code, right? So we can literally use our code and just basically do exactly this. We can basically create a time series, just like I showed you for a single snapshot. We can create lots of snapshots, and we can ask, well, what do you see? And I won't go into this in any detail, but all I'm going to try to tell you here is that this is for an outflow, right? This is all of our models are outflow models, right? All of our models are disk winds. And what I really just want you to take away from these pictures here, this is 2 particular transitions that we simulated. And what I want you to take away here is purely one thing, which is that if you remember, I said, this is what normally people look at. They say, well, outflow should look a bit like this. It should look sort of skewed towards from the bottom left to the top right. Inflow should be the opposite, and symmetric should be accretion disk. This is an outflow, okay? We know this because we made it. And the point here is really just that these simple pictures are not capturing all of the physics. And I won't go into detail of why that is, but you can hopefully see that this doesn't look anything like the sort of naive outflow picture that people usually use to interpret observations. And so one of our main conclusions from this has been that you have to be super careful when you interpret these things. These images are extremely powerful, these kind of echo images, but you have to be very careful to not overinterpret them, because you can really go wrong. You can basically end up saying something like, oh, look, this is symmetric, or this is going this direction. This must mean it can't be an outflow, or it has to be an outflow. And it's just not true, because actually the simulations show it's more complicated than that. Okay, and that's it. I've probably gone on slightly over time. But hopefully I've convinced you that these disk winds really matter and that they have a nice possibility of explaining really a lot of what we see from quasars and AGN. And hopefully that kind of gives you a sense of the kind of work that we do in this area and why we think it's important. Thank you.
Thank you, Christian. Thank you very much for that. If you've got time now, we'll just take a few questions.
Sure.
There are some coming in, and I've got a couple myself if we run out of other people's questions. Question from Harry Parks. He says, thanks, a great talk. He says, your modeling has shown a proof of principle for emission observations from different directions. What are you doing to tighten up the modeling to make a better comparison with actual observed spectra?
Yeah, it's a really great question. It's kind of for us really the $1 million question. In fact, it was kind of for us. It was always nice to do the proof of concept first because that nobody had really done that, and it was important to do that. But it's very hard to know exactly which way to go. And so the reason it's hard to do that is because first from the observational side, every single quasar and AGN is a bit different. So, you don't even entirely know what you're supposed to be modeling exactly. And then secondly, our model is sort of a combination of too simple and too complex, right? It's too simple in the sense that nobody in their right mind actually believes that disk winds are perfectly biconical or something like that, right? On the other hand, that simple model has so many free parameters that you can adjust that it's just completely unfeasible to try and explore every possible combination of parameters. So you're sort of in a tough spot here, right? Where the data is incredibly heterogeneous and diverse, and your model is probably not perfectly right and also completely impossible to explore completely. So our approach is kind of twofold, I would say. One is we're going to be trying to use the model to sort of explore trends in the data. So that's one of the most important things one learns, is that maybe every individual quasar AGN, can be a weirdo, but there are real trends overall that you can try and use to reproduce. And if your model doesn't have the right trends, maybe as a function of, black hole mass or brightness or something, then your model is probably wrong. And so we can try and do that, and we can try use this to constrain it. We are trying to also model some individual systems, and there the goal would be to take there's a few quasars and AGN for which we have extremely good constraints because they've just been endlessly studied. And so in those cases, one can hope to fix enough of the parameters of the model to actually then figure something out and to figure out, okay, the freedom of our model goes down in that case, and then we can see, can we actually reproduce this data? So those are the sort of two directions, two almost orthogonal directions that we are taking this in.
Thank you. That's a really good answer. Another question from Darryl Dobbs. He says, on average, are the outflows coming from the inner, middle, or outer part of the disk?
Again, great question, actually. That was one of the first things we had to kind of try and figure out. And typically people, when we're not the only people who have tried modeling these things. I mean, the typical idea that people have is that maybe they come out from something like 100 to a few hundred gravitational radii, which basically means, call it the middle of the disk-ish. So just to give you a bit of reference, so the inner edge of the disk is probably sitting at like maybe 6 gravitational radii, so the Schwarzschild radius would be 2. And then the outer disk probably breaks up into clumps once you hit like maybe a few thousand. So a few hundred is sort of more or less in the middle. But this is actually, for example, where reverberation mapping has come in recently. So our work on that over the last year or two has kind of started to suggest to us that actually we may have, it may have to be the case, at least in our outflow picture, that the outflows need to be a bit further away because the lags we otherwise get are not quite right. So the lags that we get in our sort of simplest models are a little bit too short. And the natural thing to fix that would be to assume that the outflows are a bit further away. So that's sort of how this kind of, again, feedback loop between observations and modeling works.
Okay, yeah, so that's really interesting too. So We don't have any other questions at the moment, so I'll just slip in one of my own. The reverberation mapping seems to be kind of really clever, very impressive observation. Could you just say a little bit more about the equipment that was used to make those? I noticed you put things in units of flux. What kind of magnitudes are we talking about, and what kind of spectrum?
Oh yeah, so that's a great question. So again, yeah, so the reverberation mapping is incredible. So funnily enough, the sort of classic reverberation mapping, where you basically where you just look at a line overall, rather than trying to break it up into blue bits and red bits. That is actually something that in principle, I would imagine even amateurs potentially could do, because you can, if you have imagine you have a narrowband H alpha filter, say, right? It really is nothing more special than taking, the brightest HVN or something you can think of that maybe, and maybe check that it's one that varies on a reasonable timescale, and you just observe it like every night for, as long as you can, in both a broadband filter and a narrowband filter. And then you can make a plot. Oops, you can make a plot. Sorry, I think never mind. Yeah, you can make a plot exactly like the one I showed you of line versus continuum, and you'll see exactly this. You just have to be very patient for most of them. So that's not so bad. And the magnitudes of those things, the brightest systems can be 13th, 15th magnitude, so that's not so crazy. However, the spectroscopic bit, where you now really look at, oh, and the blue bit is delayed by, less than the red bit. That's super hardcore. That takes the best telescopes. And in fact, I would say, so that it's only over the last maybe 5 years that observers have started doing that really well. Because the challenge that, first of all, you need extremely sensitive telescopes. Because it's, even relatively bright things, by the time you split them up into the different wavelengths, are not so bright anymore. And then secondly, the amount of time allocations you need are crazy, right? You need, even for relatively fast moving things, you need, maybe 50 nights, 100 nights or something, which is just, that's a huge allocation. So yeah, it's super expensive. The by far the best and probably the most high impact thing that happened recently in that area is where one of the pioneers of reverberation mapping, Brad Peterson, led an amazing team of people doing what's called AGN Storm. And they basically did a campaign with Hubble, where they got essentially 100 snapshots of Hubble, actually 150 snapshots, I think, of Hubble observations. And they, of course, coupled that with ground-based observations and so on, because once you get Hubble, everybody else is happy to jump on board. And that's basically been a bit of a game changer, because all of a sudden you could, like, things that were previous, it's very easy in that game to get kind of data that is barely good enough to see something, and you always wonder whether you're really seeing it or not. And and that has been a game changer, because a lot of things were all of a sudden just a lot more obvious, and you can really say, okay, now we're really seeing this, or we're really not seeing this. And that data has been just tremendous. And there's now, I think, a few campaigns like that. So it's still very much early days in that. But I would say, actually, yeah, even the basic stuff of just doing lags in broadband is actually, in narrowband filters, is already pretty cool.
Okay, I mean, that's maybe something an amateur might like to try. I mean, we do similar thing on variable nebulae, where we look at, the way that they change in their
absolutely. Like, I mean, people have looked for light echoes, essentially, and it's a different version of a light echo, really, right? It's very powerful. I mean, reverberation mapping is a really nice tool.
Okay, just there are a couple of questions have appeared whilst we've been talking about that. So one from James Dawson. He says, a lag of 1 light day equates to how long in normal time? I'm not sure what that means. How long is the delay between receiving the 2 spikes of red and blue and a lag of 100 light days?
So actually, yeah, so that's kind of nice. So the lags literally are measured in days. I mean, so essentially, when I say we measure a lag of 1 day, I really mean we measure a lag of 1 day. And
there's no relativistic.
Those corrections are, not at that level. They're not important. I mean, we're sort of lucky, of course. I mean, well, I hope we're lucky, and it's not just a selection effect, but but it turns out that these lags typically are on the order of anywhere between maybe a day and, I don't know, a month, something like that. And one of the really interesting things is, of course, that I mentioned how lines are really formed, and how, you have different, some lines come from higher energy orbits than lower, and so on. So actually what happens too is that different lines have different lags, which is kind of cool too. So, and that basically means that, one line might tell you more about high energy radiation, and it's saying that, oh yes, the high energy stuff is sitting more over here, and the lower energy stuff is sitting, the cooler stuff maybe is sitting more over here. So you can really do incredible stuff by combining this. So it's not even just pure kinematics, like the velocity of stuff is like this, but you can even try by combining this to then constrain the thermodynamics too. You can sort of say, all right, and not only is this stuff moving faster than this stuff, but the hot stuff is moving faster, and that's pretty incredible. But the typical lags, they're on the order of a few days. And then from that, we can immediately then infer that the characteristic size must then be just that number in light days.
Yeah, okay, that's good. And just one last question from David Boyd then. He says, does your modeling of QSOs inform our understanding of the behavior of active CVs, so cataclysmic variants?
Yeah, funny. Again, great question. I mean, I work on both of these things, and it's, for those of you, there might be some in the audience who actually have worked with me, know me a little bit, or from my CV work. And if you go far enough back, you'll actually notice that the code that I described there to you, the simulations that I described to you, they didn't come from quasars. They came from CVs. We used that same simulation code for CVs originally, because we wanted to model the outflows from CVs. And in fact, one of my pet things that I think the curiosity that drives my research more than anything is whether and to what extent all of this stuff, all accretion as an astrophysical process, is actually universal. Essentially, all of them, it doesn't really matter whether you observe a young stellar object or a CV or a neutron star or a black hole or a supermassive black hole. Yes, they all show some different phenomenology and different timescales and so on, but are they actually fundamentally all the same? And there's a lot of reasons to think that a lot of it really is the same. I mean, there's an awful lot of stuff, like I mentioned flickering as one example, but again, CV people will know that these emission lines, we see the same emission lines in CVs. If I showed you a spectrum without telling you the overall flux scales, you wouldn't be able to necessarily tell the difference between a quasar and a CV sometimes. So yes, absolutely. For me, I'm one of the people, my research on one is always informed by work on the other. And in fact, I use the same tools for both. Not everybody's like this. I think, to be fair, I think my background in CVs, I think, is one of the sort of more unique things. Like I'm not an expert in many things, but one of the useful things that I think I can bring to the quasar work is actually a background in other things, because that is not something people sometimes have. I think quasar researchers are sometimes surprised by how much we've learned about accretion physics, for example, in the much smaller settings, where of course we can study them in much more detail. So yeah, absolutely, very close connection.
Yeah, that's really interesting to hear. So thank you very much for a really, really interesting talk and some amazing observations, I think, right at the kind of limit of what modern astronomy can do. Yeah, thank you very much. So
thank you.
I don't know if Alan is still on. I think he's probably not. So I'll thank you on behalf of the BAA for your talk.
No problem.
Thank you very much.
It's been a pleasure. Thank you.
Bye. And we've got a second talk coming up at 2 p.m. Professor Clive Tadhunter's talking about black holes, quasars, and the evolution of galaxies. So join us again then. Thank you very much.